After learning all about complex numbers and how to apply operations to them and how to simplify expressions involving imaginary numbers, it's time to now determine what's the relationship to trigonometry. So we started off our lesson with complex numbers by remembering the real number line. Now remember that this is a number line that has all of the natural numbers, 1, 2, 3. It's got all of the integers, being the negative and positive whole numbers, and 0. It's got fractions of 1/2, square roots, pi. So it's got all of these different numbers. So if I wanted to plot one of our values, let's say I wanted to plot pi, then I would just put a dot at pi right here. Or if I wanted to plot -2, I would put a dot back at -2 to show that I'm able to get to those particular locations along the real axis. So we can now plot basically any real numbers that we choose. If I want to plot -2, then I can do so. If I want to plot 3, I can do so. But what if I wanted to plot an imaginary number? The problem is that imaginary numbers cannot be located on the real axis. So we need this other axis that's somewhat of in a different realm, a different direction, a different dimension, if you will. And so what we do is we're going to add a different axis. Okay. When we add this axis here, we're going to refer to this axis as the imaginary axis. Now I realize that it looks like the X and Y coordinate system. But all we're doing at this point is creating a new way to visualize imaginary and complex numbers. So if I think about this as the imaginary axis and I start counting upwards, I don't say 1, 2, 3. Instead, I realize that this is I and 2I and 3I. And likewise down here, this would be -I and -2I and -3I. So I can plot all of my imaginary numbers along the imaginary axis and all of my real numbers along the real axis. So now I can plot numbers like I or -3I. And so if I wanted to plot the value of, let's say, -2, -2 would be on the real axis, and therefore it wouldn't be up or above or below that axis because it's a real number. And if I wanted to plot the number 3, I would come over here to 3, and it's on my real axis. But if I then wanted to plot I would have to plot the number on the imaginary axis because it's not a real number. So I see that it's going to be somewhere else besides on the real number line, and this down here would be -3I. Now we're going to take a step further and realize that all of these are technically complex numbers because they're all in the form of A plus BI. All real numbers just have no imaginary part, and all imaginary numbers have no real part. And so if every one of these numbers could be listed as A plus BI, then notice that this means go -2 in the real direction and 0 in the imaginary direction. This means go 0 in the real direction, but go -3 in the imaginary direction. Which is why when we actually plot new points here, let's say we wanted to plot the point 2 plus 2I, or 3, -3 minus I. If I wanted to plot those, then that would mean that I should go 2 units in the real direction and 2 units in the imaginary direction. So that means that I can actually plot my point 2 plus 2I as some point in this direction here, while -3 minus I would put me back -3 in the real direction and -I in the imaginary direction. But this isn't actually all, because what if I wanted to now graph this complex number down here, which is the sum of two other complex numbers? Well, let's start off by looking at 2 plus I. 2 plus I would be this location. And 1 plus 2i would be 1 in the real direction and 2i in the imaginary direction. And apparently, if I add those two results together, my final result becomes the complex number 3 plus 3i. So if we look at where 3 plus 3i is, that's way up here at the real number of 3 and the imaginary number of 3i. So if we now look at this, how could we think of this graphically? Well, now that we've learned about vectors, turns out that we could think about this number, 2 plus I, as being the vector that extends from the origin out to that point. So instead of just plotting a point and saying that's the point 2 plus I, what we're going to do is represent these complex numbers as vectors in the complex plane. So this right here is referred to as the complex plane. So even though it looks like our Cartesian coordinate plane with an x and y axis, it's actually much different. And so likewise, I wouldn't just say that this point down here is negative 3i, I would actually draw a vector to negative 3i, or draw a vector up to I, right? Or on our x-axis, if it's a real number, I would draw a vector out to the real number of 3, or a vector out to the real number of negative 2. So now if we take a look at the number 1 plus 2i, 1 plus 2i is this number right here, 1 plus 2i, which has this vector. Well, let's remember how we add vectors together. We add vectors by picking one vector up and putting it onto the other. So why don't we pick up this vector and start at the terminal point of 2 plus I. I would then move 1 unit in the real direction, 2 I units in the imaginary direction, and therefore this would be the sum of the 2 points. So if I now take this vector, or this number rather, as being 2 plus I, and this number as being the number 1 plus 2i, it just doesn't start at the origin, but notice that it's parallel to it, then I could see that the resultant is the answer that I'm after, which is 3 plus 3i. So it appears that graphically, we can actually show the process of adding and subtracting vectors, or I'm sorry, adding and subtracting complex numbers simply by demonstrating vectors. So if we now take a look at this point in, or rather this vector in the xy plane. So if we were to think of this as the xy plane, then notice that point would be the point xy. And that would simply be because obviously if I drop this down, we could see that the vector forms an angle of theta. It gives us a certain x coordinate and a certain y coordinate. And we could replace that hypotenuse with r, very similar to the way that we developed our trigonometric functions at the very beginning of trigonometry. But now, what if we were to think of this not in terms of the x and y axis, but in terms of the real and the imaginary axis? Then that point would no longer be an ordered pair. It would be a complex number that's x units in the real direction plus yi units in the imaginary direction. So now we have this vector, this vector x plus yi, that extends somewhere in my 360-degree rotation And it's defined, all complex numbers can be defined as x plus yi. Now there are a few relationships that we can see in this triangle here, is that we know that the x coordinate can be found, well, we can recognize first of all that x over r is the value of cosine theta. And we also know that y over r is the value of sine theta. So if I multiply both sides by r, that ends up showing me that my x coordinate is r cosine theta, and my y coordinate is r sine theta. All right, which really means that we could also rewrite this. We could rewrite x plus yi as r cosine theta plus r sine theta I. So this right here is technically what we refer to as trigonometric form of a complex number, but it turns out that there's a slightly different way that we could write this as well. Okay, if we were to factor out an r, we could rewrite x plus yi as r times cosine theta plus sine theta times I. But because I don't want to get confused about the fact that sine theta I might have the I inside attached to theta, we avoid that kind of ambiguity by just putting the I in front, and we rewrite it as r cosine theta, r times cosine theta plus I sine theta. So all complex numbers in the form x plus yi or a plus bi can all be written in what we refer to as trigonometric form. Now it's really important to realize as well that the angle that we refer to is always going to have to be an angle between 0 and 360. So we want to make sure that our angle is somewhere on one rotation. So it's somewhere between 0 and 360 degrees. Now there's one more form of this actually that we could write as a shorthand notation. And the way that we write this is just by recognizing that I'm going to be writing cosine theta every single time and sine theta every single time. So as a shorthand notation, we can actually write the c from cosine, the I being imaginary, and the s from sine, in order to rewrite this form as r cis theta. And this is actually the same exact notation, it's the same exact meaning, but we have r cis theta, cis, simply describes the fact that this is a complex number. Okay. All right, so let's try a couple examples. So here we have a complex number in trigonometric or in polar form, where we know that this is the same as r cis theta. And what we're trying to do is turn it into rectangular form, which is x plus yi. Rectangular because we can draw it on the rectangular coordinate system. And so our goal then is to find what x and y are. Now this is the relationship you have to remember. You've got to remember that x is equal to r cosine theta, and y is equal to r sine theta. So if I want to find those x's and y's separately here, then that just simply means that I've got to rewrite this as 2 cosine, I guess we could write it as 2 cis 300 is the same thing as saying 2 times cosine of 300 degrees plus I, or rather 2i, times sine of 300 degrees. And so that's going to tell me what my x and my yi are. So this right here is my x, and this is my yi. So we could find those both separately and recognize that x is simply 2 times cosine of 300 degrees, and y is 2 times sine of 300 degrees. Now remember, 300 degrees is in the fourth quadrant. It's a steep angle in the fourth quadrant. So we're left with x equals 2 times the cosine of that is positive 1/2. And sine of 300 is negative square root of 3/2. So that means that if this quantity here gives me x equals 1, and this quantity gives me y equals negative √3, then I should be able to see that this point, 2 cis theta, 2 cis 300 degrees, can actually be rewritten as 1 minus the square root of 3i. And that is my result. Now I'd like to take a look at this if we were to see this just on a graph and recognize why this makes sense. So if I were to take a look at 2 cis 300, that would simply mean to start with the 300 degree angle, which is down in the fourth quadrant. So here's our 300 degree angle. Okay, but because of the fact that it said 2, then that means that I'm going to go 2 units outwards at the angle of 300 degrees. But now if we look at this in terms of a reference triangle, by drawing up to our x-axis, then we can see that this is actually a reference angle of 60 degrees, which would complete the 360 degree rotation. So this is a 30, 60, 90 triangle. So if that's the case, and the hypotenuse is 2, remember that the shortest side is 1, and the longer side is √3. But because I went downwards, it's negative √3, which is why this should make total sense that even though we drew 2 cis 300 to begin with, this was actually the complex number 1 minus the square root of 3i. Going back to the page of our derivation here, we should recognize that these two formulas can be used to convert from r's and thetas, or trigonometric form, by being given r and theta, we can turn it into rectangular form. So this is often helpful, knowing that x is r cosine theta and y is r sine theta. But notice that there are other relationships in this triangle as well. For instance, we know that tangent of theta is equal to y over x. And we also know that by the Pythagorean theorem, x squared plus y squared equals r squared. So r is the square root of x squared plus y squared. Well, the advantage of those two equations is that I could be given x's and y's and find theta, or given x's and y's, find r. So these two formulas are helpful in turning from rectangular form into trigonometric form. So these three formulas, or four formulas rather, are very important to switch forms. Now I keep calling these trigonometric form. I'd also like to share that another word for this is polar form, going along with what we refer to as polar coordinates that we're going to see very soon. Okay, and so let's take a look at how we can start with how we could start with rectangular form and turn into polar form. So in this situation, we're trying to convert this form, which is x plus yi, Also recognizing that the y value is 1i. We're trying to convert this into polar form, which is r cis theta. So we have to start with the values of x and y and somehow find my r cis theta. Now, before beginning, we should try to think first about, again, what quadrant we're in. So because we went negative root 3, we're back here, and positive 1 is up the y-axis. So that means that we have this angle that's going to be somewhere in the second quadrant. Okay. Which means that my theta should be somewhere between pi over 2 and pi, or 90 degrees and 180 degrees. So let's start off with recognizing that x is root 3 and y is negative 1. So with that information, we could find out that tangent of theta is equal to y over x. Or if we rationalize the denominator, that becomes negative square root of 3 over 3. All right, well, we should see from here that that means that theta, if I have a tangent value that's negative, I know that that's either going to be in quadrant 2 or in quadrant 4. So I can see that root 3 over 3 occurs at our pi over 6 angles. So the second pi over 6, second quadrant pi over 6 angle is 5 pi over 6. Or the fourth quadrant pi over 6 angle is 11 pi over 6. This is why it's important to recognize, based on the signs, what quadrant we must be in. So that must mean that my angle is 5 pi over 6. So I already see that my answer here is going to be r cis 5 pi over 6. I've just got to find what my r value is now. Well, remember that r is the square root of x squared plus y squared. So root 3 squared plus negative 1 squared. Well, that gives me that r is equal to the square root of 3 plus 1, which is 4. Square root of 4 gives me 2. So that means that r is equal to 2. Well, if r is equal to 2, then that means I can come back here and see that my r value is 2. So 2 cis 5 pi over 6 is the same thing as negative root 3 plus I. But again, this should make sense. If we were to look at this as a right triangle, if that's 5 pi over 6, then that must mean that this is pi over 6, or 30 degrees. And therefore, we have a 30-degree right triangle. So that must mean that in this case here, if this is negative root 3, and this is positive 1, then the hypotenuse is 2, and therefore 2 units away from the origin. So we've got multiple ways to write this. And if we wanted to write this in the exact form as opposed to the shorthand notation, we could write it as 2 cosine of 5 pi over 6 plus I sine of 5 pi over 6. Or if we wanted to write it in terms of degrees, we could do the same thing. We could write it as 2 times cosine of 150 degrees plus I sine of 150 degrees. So this is just another form of being able to write a plus bi, or x plus yi. We could write them in either form, either write it in rectangular form or write it in trigonometric or polar form. Now it turns out that in order to apply operations with these complex numbers, it's going to be really simple for us to do so if it is in polar form. Now, the last thing we want to discuss here is just this idea of a complex number in the imaginary, real and imaginary, or the complex plane. So when we have our real and imaginary axis here, and we plot some point in the complex plane, then that vector is describing some point A plus BI. We often refer to complex numbers by the variable z. So when I see z in terms of complex numbers, that's referring to some number A plus BI. Now, z has a particular distance away from the origin as well. So when we refer to the absolute value of z, okay, which again you could think of as the absolute value of z, or as the absolute value of A plus BI. What we mean by that is the distance from the origin. Okay, so all this means right here is the magnitude of that vector. So when we refer to the absolute value of a complex number, what that's really saying is, how far is it from the origin? How far is it from 0, 0? So in other words, the absolute value of z is equal to the square root of a squared plus b squared. And therefore, we can now see why we put the magnitude symbol as the absolute value. The absolute value is nothing more than just telling me how far that complex number is from the origin. In other words, this length is the absolute value of z. So it's really just the same value as r. You could think about the absolute value of z as being the same value as r, right? So notice that it has the same formula, but it's just a different way of describing it. And therefore, oftentimes when we say the absolute value of a complex number, that's what we're referring to. So now in the next sections, we're going to be able to look at how we can multiply these complex numbers, divide these complex numbers, raise these complex numbers to powers without having to go through the whole process of expanding our A plus BI times another complex number, but instead how we're going to be able to use the new polar form, r cis theta, in order to make our lives a lot easier.